Hello students, in the last lecture we discussed modulus of complex numbers and some basic inequalities. In this lecture we will discuss polar representation of complex number. So let us start with the complex number z equal to x plus iy, where x and y from real numbers. Once we are given with a complex number, we know that we can associate this to a ordered pair x comma y. It means that we can associate this point in the plane. Let us call this as the point z, which is x plus iy, where x going to denote what is the magnitude in the x axis when we project this point in the x axis, and similarly the magnitude of this in the vertical direction, which is y. Now what we observe here is, given any complex number, we associate a point in the Cartesian plane, and this is standardly taken as x axis, but in the interpretation of complex numbers in the plane we can treat this as the real axis, and here this is imaginary axis. And now in this plane, for each point we associated a complex number, and such a complex number plane is called Argand plane or complex plane. Now given any point in the plane, we can also determine this point if we know the distance from the origin. Let us call it as r, and theta, which is angle made to the positive x axis. So let us call it as, this is origin 0 comma 0 or the complex number 0, and let us call this as point P. Now what we are saying is, r denotes distance from the origin, we are calling the point O, to the point P, and theta is denotes the angle between the line joining segment OP and positive x axis or the real axis. So if we are given that r and theta, then we can determine what is this x, which is simply write down the relation, that is cos theta is given by adjacent by hypotenuse. So we get x as r cos theta. Similarly we can see that y is r sin theta. So what we are observing, if the distance and the angle is r given, then x is written by x r cos theta and y is given by r sin theta. So it means that our complex number z can be written as z equal to r cos theta plus I r sin theta, where r is the distance from the origin to the point z, so which is non-negative, and theta can be taken as from 0 to 2 pi, and further this can be written as r times cos theta plus I sin theta, and such a representation is called polar representation. This representation is called the polar representation of z. So, again let me just recall. If we know the components x comma y, we are associating a point in the plane, and further this point can be just equivalently determined by the distance from the origin and the angle theta. So, here we get the factor that is r and theta, which is called polar coordinate system. Which is just the distance from the origin and the angle, and the what we are familiar is Cartesian coordinate system, which is x comma y. Suppose r and theta is given. So, we start with suppose given r and theta, then we see that we can associate the point in the Cartesian coordinate system as r cos theta and y as r sin theta. Conversely, suppose we are given with x comma y. Now, question is how do we get this r and theta? We can again just go back to this picture. By Pythagoras theorem, we could immediately realize r is nothing but square root of x square plus y square. So, given x y, the distance from the origin is straightforward. R is given by square root of x square plus y square, and theta, what we observe is cos theta is x by r and sin theta is y by r. So, we see that the theta should satisfy these two equations simultaneously. So, by combining these two equations, we see that theta must satisfy this equation, that is tan theta equal to y by x. Now, still like this particular point is not clear, that immediately how do we calculate the value of theta if x and y is given. So, I will make some simple remarks. So, in order to calculate the theta. So, before going to that, let me introduce some notations. We write the complex number in the polar representation, that is r cos theta plus r I sin theta, which is thus, and we can write it as r times cis theta, where the cis theta is cos theta plus I sin theta, and theta is denoted by argument of complex number z, and we also observe that r is nothing but just the modulus of z, which is the observation. Now, some simple remarks. What we observe is, once we start with the polar representation cos theta plus I sin theta, by periodicity of cos and sin function, what we observe is this can be written as theta plus 2k pi plus I times theta plus 2k pi where k is in the integers. It means that when I take r theta, or if I take theta plus 2k pi, they map to one element, which is x r cos theta and y as r sin theta. In other words, what we observe is, if theta differs by 2 pi, still they map to the same point, which is x y. How do we understand this? By geometrically. So, we have a point which gives the theta angle from the positive x axis. Now, the same line can be measured as you go one cycle by 2 pi and then further this theta, which means this is theta plus 2 pi. Again it denotes the same line as angle as theta plus 2 pi. Similarly, if you take any k multiples of 2 pi with k being positive integer, we could see that we go around by 2 pi multiples, which means we again come to this initial line, then we add this angle theta. So, geometrically what we observe is it represents the same line if we take the theta plus 2k pi. Now, question is, how about the negative values of k? Let us see that. So, we have a line which makes the angle theta. Now, in the observation that this is something which is r comma theta in the polar coordinate system, what we are saying is this is same as r theta minus 2 pi. I am just considering with the negative value k, that is k as minus 1. Now, this can be seen as I measure the angle in the other direction, that is the clockwise direction, which makes it minus 2 pi, and then I add an angle which is theta. So, in other words, what we are making here a convention is, when we measure an angle between two lines. We fixed our x axis as theta equal to 0, and if you measure in the anti-clockwise direction, theta is treated as positive radians, and if we measure in the other direction, which is the clockwise direction, then the angle which is measured in the negative radians. Let us see whether it is consistent with our representation. Suppose I start with, let us say, a point which is 1 plus I. Let us calculate what is the angle and distance. Distance is square root of 1 plus 1, which is 2, and theta by the relation which is tan theta is y by x. Here y is 1 and x is unit 1. So, we see that theta is pi by 4, and now what we are meaning by minus theta is in the opposite direction, which means that minus pi by 4, if you measure from the other side, which is like minus pi by 4, which is nothing but a reflection of this line with respect to the real axis. So, if we do the reflection, this will give us nothing but the z bar, which is 1 minus I, but let us see whether it consistent with the polar representation. I started z as this 1 plus I. If I write the polar representation, r is root 2 and the angle which is pi by 4. Now, we consider a point, let us say consider minus theta point, that is root 2 cos of minus pi by 4 plus I sin pi by 4. Cos is a even function and sin is a odd function. What do we get as, which is root 2 times, which is cos pi by 4 minus I sin pi by 4, which we get nothing but as z bar. Okay. So, this example illustrates that if we measure angle in the anti-clockwise direction, we measure in the positive radians, and if we measure the angle in the clockwise direction, we measure in the negative radians, which is exactly represents like the conjugation that we are able to see with the polar representation as well. Let us generalize this example. So, suppose we have a point in the complex plane z which is with the angle theta. Now, we take its exactly the reflection which is z bar. Now, we know that it is angle is theta, but our convention we measure it as minus theta. Let us see what is the polar representation we get. Here it is r cos theta plus I sin theta. By definition, taking this as an angle, then we get something which is like z prime, which is a complex number given by angle minus theta, which is r cos of minus theta plus I sin of minus theta. Then immediately we observe that this is nothing but z bar. So, this point explains that what is the meaning of taking say r plus theta plus 2k pi with k varying in the integers with even the negative numbers. We see that it maps to one number in the Cartesian coordinate system, which is r cos theta and y as r sin theta. Now, again what we are trying to do, our interest is for each point in the complex plane we would like to give a different representation in terms of r and theta. Now, we observe that theta can be taken as theta plus 2k pi, which also represents the same point. At the same time, to cover this entire plane, what we need to do is we need to vary theta for 2 pi interval length. It means that you take a theta with theta naught to theta naught plus 2 pi, where theta naught can be any real number. If we vary our theta in this region, then it covers the entire plane. Therefore, what is important is the argument must vary in a 2 pi interval. So, the conventional one is you consider theta naught as 0, which we get it as 0 to 2 pi. If we recall again, thus it means that we start with the initial segment as positive x axis where theta is 0, and then you measure in the positive orientation, that is anti-clockwise, with a rotation of 2 pi. So, which covers the entire plane. And another standard one is minus pi to plus pi. So, now here in the entire discussion, positive x axis always as theta as 0. This particular line is always x axis, always consider theta as 0. Now, we know what is the meaning of the positive radiance, which means you start from 0 and then come this cycle, which is here this line, which is theta as pi, and other region we cover by going clockwise direction. So, here this particular line, if we measure, this will be theta as minus pi. So, we observe that the interval length is 2 pi, and if we vary our theta in this interval, then we cover this entire plane, and the considering the angle in this region, which is called as principal angle or principal argument, and of z, which is a theta which lies in the interval minus pi to plus pi. We would like to ask, what is the polar representation for the point origin? You consider the origin. Now, as we discussed, what we do is we take a line which starts from 0 and pass through the point. Okay. So, if you take any line starts from 0 and anyway it pass through 0 as well. So, which means we can take any line which starts from 0 and r is the distance from origin to the point, which is itself, which means r is 0, but if I take the theta, any line pass through the 0, which we are going to take the as the angle. So, which means since the all lines basically from 0 whichever pass through, it contains 0, which means theta can be arbitrary here. Theta is can be any. It means that if I take r equal to 0 and theta can be any value, represents the origin. It means that we do not have well defined polar representation for the origin. So, one need to be careful with respect to the origin point. We do not have a well defined representation with respect to the polar coordinate system. Now, we are close to discuss about how to calculate the theta value. So, to get a unique value for this, we restricted ourselves in the principal argument, that is theta is minus pi to pi. Now, there is one more issue, that is tan is periodic with period pi. So, to get this calculation, we need to do some adjustment with respect to the quadrants where x and y lies in. Formula for principal argument of z. First observation is tan is a periodic function with period pi, which can be easily verified, or in general what we have, tan of x plus k pi, which is tan x for k in integers. if we try to find, so our interest is to find the principal argument such that tan of theta is y by x, but by the above relation we see that theta will be given as tan inverse of y by x, which going to involve, say, with the angle plus k pi, where k is in the integers. So, to avoid this multi-valued, again we restrict the value of tan inverse to the interval minus pi by 2 to pi by 2. So, restrict tan inverse of y by x in the interval minus pi by 2 to plus pi by 2, which we call it as arc tan of y by x, that is arc tan function means that it is inverse function of tan such that the value is restrict to the interval minus pi by 2 to plus pi by 2. So, therefore, theta is arc tan of y by x, and we need to make a proper adjustment by some multiple of pi. So, we will discuss now how to adjust some value of k plus such that we get our principal argument of given complex number z. So, our principal argument formula, that is argument of z is given by arc tan of y by x plus k plus pi, where k plus, which is proper adjustment depending on the where our x y lies in. So, k plus is 0 if x y lies in the first and fourth quadrant, which is given by x is positive or y is and y is positive, or same the fourth quadrant y is less than or equal to 0. So, for both cases we see that the value for k plus we do not need to adjust here, because the arc tan inverse going to give value between minus pi by 2 to plus pi by 2, which covers the first and fourth quadrant, first quadrant and this is fourth quadrant. And if x y lies in the second quadrant, which is x is negative and y is non negative, we add pi to the obtained value arc tan of y by x, and minus 1 if x y lies in the third quadrant. So, what we are missing here is x equal to 0, if x equal to 0, then it is the y axis, and we know that, say if x equal to 0, non-zero, we get this formula. If x equal to 0, then argument of z is pi by 2. If y is positive, negative, we take minus pi by 2. Let us see a simple examples. Suppose we are given, say minus 1 plus I. Now R is, say Z is minus 1 plus I, then R is given by square root of 1 plus 1, which is root 2, and the principal argument theta is given by arc tan of y by x plus the k plus pi, where the point lies in the second quadrant. So, we take k value as 1, so this is minus pi by 4 plus pi, we get that 3 pi by 4. So, similarly you can calculate for other complex numbers, which is z as root 2 plus 2 root 3 I. Calculate what is its polar representation by calculating r and theta. Let me summarize the formula for principal argument of z. Suppose the point lies in first and fourth quadrant, then just the arc tan of y by x, and if it is in the second quadrant, arc tan of y by x plus pi. If it is in the third quadrant, arc tan of y by x minus pi. Let us do one more example. Suppose we are given a complex number z as 1 plus cos A plus I sin A, where A lies in the interval 2 pi. Now, we would like to calculate or find a polar representation for these complex numbers. So, let us just notice that this is not in the polar representation form. So, to convert, so first calculate r. R is given by square root of x square plus y square, which is 1 plus cos A the whole square plus sin square A, which is cos square A plus sin square A we have here. So, we get 2 times 2 cos A, which is 2 times 1 plus cos A, which is, by trigonometric formula we see that this is 2 times of cos square A by 2, and we get the r as 2 times modulus of cos A by 2 r equal to 2 times modulus of cos a by 2, and argument theta we will calculate accordingly to the formula. So, for a in the interval 0 to pi, we see that z is in the first quadrant, which means that the theta directly the arc tan of y by x. Let us calculate the arc tan of y by x sin a by 1 plus cos a, which we get it as this is 2 times sin a by 2 cos a by 2 by 2 times cos square a by 2. This is nothing but arc tan of a by 2. Now, notice that since a is in the interval 0 to pi, a by 2 is in the interval 0 to pi by 2. So, the arc tan gives just as it is a by 2. For you, the other simple exercises, if a lies in the interval pi to 2 pi, just show that or derive that theta is a by 2 minus pi. Verify that theta is a by 2 minus pi. Therefore, z is written by 2 times modulus of cos a by 2 with cis the angle is, which is going to vary, cis of a by 2 if a lies between 0 to pi, and for other region a by 2 minus pi. So, for the value a equal to pi, we can notice that z is 1 plus cos pi plus I sin pi, which is 0, and 0 has no unique polar representation. So, with these examples, let us move to multiplication of complex number using polar representation. Suppose we have two complex numbers z1, z2 with polar representation r1 cis theta 1 and z2 r2 cis theta 2. Now, if we multiply these two just by the usual complex number multiplication, we can notice that this is r1 r2. Here we have cos I sin theta 1 and similarly here the factor cos theta 2 plus I sin theta 2, their product comes as cos of theta 1 cos of theta 2 minus sin theta 1 sin theta 2 plus I times cos theta 1 sin theta 2 plus sin theta 1 cos theta 2, and by the trigonometric formula we can see that this factor is cos of theta 1 plus theta 2 plus I times sin of theta 1 plus theta 2. This can be written in our notation cis theta 1 plus theta 2. So, we made an important observation that the multiplication of two complex numbers become simple if we do in the polar representation, that is when we multiply z1 over z2, we scale the z2 by the factor r1 and we rotate by a angle which is theta 1 with respect to the origin. So, what we observe here as like modulus of the product of two complex number by polar representation, we see that the modulus is nothing but r1 r2 and again r1 is nothing but mod z1, other factor is mod z2. So, we see that the identity very easily we are able to realize modulus of z1 z2 is nothing but modulus of z1 multiplied by mod z2, and the argument of z1 z2. So, since we try to consider the principal argument, so it may happen that when we do the sum of two angles it may go more than pi or else it can go below than minus pi. So, in order to get the principal argument we need to do some adjustment. Let us see what is that adjustment need to be made. So, argument of z1 z2, when we multiply we get the sum of principal argument of z1 argument of z2 and we need to make a adjustment which is k plus times 2 pi, where k plus is given by the values if suppose the argument of z1 and argument of z2 sum, suppose they lie within the principal argument range, then no need to change anything, but if it is more than or less than the minus pi, say it is less than say minus pi, then we need to add, which means k plus is 1, and if it crosses the range then we need to subtract by 2 pi. Is less than or equal to minus pi greater than pi. Let us do a simple example. Consider z1 as 1 plus I, z2 as root 3 plus I. So, the multiplication we do by converting to the polar coordinates. Here we know the what is the r, which is root 2, and the angle is pi by 4, which we have already calculated, and here the modulus is 2 and we can calculate its angle, which you can verify that it is pi by 6, and then their product becomes just the scale the modulus cis and the sum these angles, which is 4 pi by 12. De Moivre's formula, which states that if z is r cos theta plus I sin theta, then the z power n is simply r n cos n theta plus I sin n theta, for n being greater than or equal to 1. So, the formula is very easily derived from the multiplication what we observed. For example, if you take z square, which means n equal to 2, which is z into z, which says that scale the modulus factor, that is r square, and sum the arguments, which we get it as cos 2 theta plus I sin 2 theta. So, by induction we can verify that z power n is nothing but r power n multiplied by cis n theta. So, let us do a simple example, which is say z as 1 plus I, calculate z to the power say 1000. Then by say we would like to calculate this. If we do the direct multiplication, then computationally may not be easier, but we see that if you go to the polar representation, which is root 2 and cis pi by 4, and now just the De Moivre's formula says that take the powers to r, which we get it as 2 power 500, and then just the cis 1000 times pi by 4, which is say 250 pi, and which we know that it is just 1. One simple exercise for you, that is prove the following identity: sin 5 theta equal to 16 sin power 5 theta minus 20 sin cube theta plus 5 sin theta, and cos 5 theta is given by 16 cos power 5 theta minus 20 cos cube theta plus 5 cos theta. Hint is just use that cis 5 theta is cis theta power 5. In this lecture we discussed the polar representation of complex number, and we observe that the multiplication becomes simple if we use the polar representation, and in the next lecture we will discuss the again further results on this.